All right, so how about we stop a little bit and then we change pace and let's talk about something more interesting, right? Let's leave the mechanics of physics and movement and loading textures and shapes and 3D objects to the side, and let's just change our pace a little bit and let's talk about something else. Look, there is one aspect of the PlayStation that we haven't touched yet at all, which is audio, right? And remember how Ken Kutaragi was involved in creating sound chips for Nintendo, right? There was this little overlap with Nintendo. He helped to design the Super Nintendo sound chip. It is no surprise, right? Since Kutaragi was leading the PlayStation project, it is no surprise that the PlayStation is a super powerful audio machine, right? And of course, at the center of the stage of this audio machine, we have the SPU, which is integrated circuit responsible for sound processing. This chip knows how to do some frequency modulation, pitch modulation, reverb, loop. There is some effects that knows how to perform. It can play some audio samples, but ultimately, right, the SPU, we need to see the SPU as this dedicated chip that knows how to get digital signals and transform that, right? Send those transformed signals to the output to be played by the TV speaker, right? So the TV speaker can do its job, vibrate and produce sound, or even headphones if you have, right? So you have these devices, these analog devices that can generate actual vibration of waves so we can hear things. We're going to basically look at the SPU, but also how to communicate with the SPU. So how do we go and we orchestrate to send the signals to the SPUs, right? So how do we send data from CPU to SPU or directly from the CD subsystem to the SPU to emit sounds, right? And of course, the SPU is not alone. We need to have a little buffer, which is, right, that memory that we have. We have 512 kilobytes of DRAM, and that is our sound memory, right? We have this kind of sound memory that we can go and store, so we can kind of buffer this data to the SPU. We can send data from the CPU to the sound buffer, and then we can play this value. So we're going to have this memory companion to the SPU, which is our sound RAM, right? Which is using this circuit, which is DRAM, right? It uses DRAM. We have 512 kilobytes. It's not really a lot, right? If we compare to modern, the capacity of modern soundboards and stuff like that, but we're gonna work with these things, right? Playing sound effects, playing actual CD tracks. We're gonna learn how to play CD tracks. So we're gonna take a look at this thing right here. Look, this board that I'm showing right here, this is the PU7, right, which was used by the SCPH 100X and 100 others. But this configuration, the location of the SPU and the location of the DRAM, it is specifically for this type of motherboard right here, right? Different motherboards, they will have different locations for the SPU and for the DRAM of the sound chip. But the purpose of these chips are going to be the same regardless of where they are located in these different boards, all right? So I'm looking at this one, right? The first one as it left Japan, right? It was used in Japan. The first one, this is the PU7 board with this configuration of chips, all right? So just to leave things written down, whenever we speak about the SPU, right, the sound processing unit of the PlayStation, is basically the same idea as any sound processing units of previous consoles, right? The NES, the Super NES, the Sega Mega Drive. The SPU is responsible for getting all this digital information, right? These digital signals, and then transforming, converting those things into actual vibrations, right? Analog signals that then the TV speaker or the headphone can go and produce, emit those sounds so we can actually hear them, right? To this medium, which is air. And speaking of which, I am not going to waste too much time here in video explaining sound theory, right? Audio theory, waves, amplitude, frequency, modulation. What I'm going to do is, I am going to leave these things written down. So in a future lecture, I'm going to actually write down a little bit more of the theory of sound, right? So what does it mean for us to have a wave, amplitude, frequency, modulation? So this type of things, I think, remember, right, as we spoke in the beginning of our course, some things are better if I explain and we have this conversation and I move my hands and point out things, but other stuff I think is better if we just leave written down. And I think the theory of sound and the theory of waves, wave generation, analog, digital audio, maybe we can just leave these things written down in a little small article that you can go read at your own time and really digest that information. I think leaving that written down is a lot better than just talking right here, right? So let's just do that. So coming back here to the SPU, let's talk about some of the specifications of this chip and what it's able to do, right? Remember in the beginning sections, we spoke that the SPU can use 24 channels, right? So we have 24 channels available for us, and these channels, they are of 16-bit ADPCM samples. And I'm going to explain very soon what these ADPCM samples mean, right? What is this format of samples? ADPCM is a way of us compressing these samples. So it is not just raw wave data, right? It is not just raw audio signals. We have a way of encoding and compressing a little bit these samples, and we're going to speak about that very, very soon. But we do have 24 channels. We also have a sampling rate of 44.1 kilohertz, right? So which is basically audio CD quality. And also, right, the SPU, this chip that we have in the PlayStation, it is capable of producing some effects. So we can have pitch modulation, meaning that we don't need to have, if we just have a change of pitch, right, so going from low to high, right, this change of pitch, we don't need to have an extra sample sending to the SPU. We can use the same sample, and then the SPU chip knows how to modulate and change the pitch of that sample. So we can do that real time. It saves us a little bit more memory, so we can just kind of do that on the fly. Right, so that is the idea of having pitch modulation, also frequency modulation, and we're going to speak about the difference between pitch and frequency very soon. We have also the effect of ADSR envelope, and ADSR is the acronym for attack, decay, sustain, and release. So we have this envelope of what happens whenever we play a sample, right? So what is the attack effect, the decay of the sample, the sustain effect of the sample, and also the release effect of that sample. So we have ADSR envelope configuration as well. We also have effects of looping and digital reverb, which was also very important for the PlayStation. So all these effects, I'm just giving a very high-level information, but everything has to do with this real-time processing sound, right? Changing that digital sound data to add reverb, looping, ADSR envelope, changing the pitch, changing the frequency, and also playing several channels, also several voices, right? You will see people talk about the different voices that we can play basically at the same time. And we have 24 channels to do that. And speaking about voices, channels, right? Remember that we can send some sample, right? Some audio sample, let's say someone saying
3, 2, 1, go!
That can be one voice channel. And then we can send that sample to the SPU, and that is going to be one of the voices. We can have several voices, right? The SPU can play these several voices at the same time. And as I said, these samples right here, they are in a format called ADPCM encoding, right? So the format of the samples, it is ADPCM. You will see that we have two types of samples, ADPCM. It can be SPU ADPCM or XA ADPCM. So they are these two different formats. We are going to talk about them very soon. But let me quickly talk about ADPCM and what does it really mean for us to have this almost like a compression method. So let's just compare to the raw alternative. So whenever we talk about sound sampling, and the word sample means how many times we go and we analyze that input, right? So how many times per minute, how many times per second we go and we sample that audio input. That has to do with the frequency of the sample, right? So look at that image right there. Do you see how we have this timeline? And depending on the sample rate that we have, we're going to go and get that input at different times. Then we can have more sample or less sample, right? The frequency of that sample. Sample means how many times we're going to go and sample something from that signal. So if we have that audio signal coming, we're going to go and we're going to sample at each time interval that we have. And usually whenever you have no compression and you just want to get the raw input from that audio signal, we use something called PCM, which is called pulse code modulation. It is no surprise, which is the simplest case. It is purely uncompressed audio, you can think of it as, the vanilla wave format that we have for files, right? Uncompressed, just the raw signal as it comes from the audio signal. So the original pure audio signal is sampled and stored digitally as it comes, right? As is. And you can see right here in this graph, let's say that the audio signal is this one right here, right? This is the pure audio signal. We're going to sample this at a certain rate, so several times here per second, let's say, and we're going to get the correct input value at each one of these sample intervals, right? So this is pulse code modulation, PCM, as raw as it gets, uncompressed audio, right? As I said, several wave formats, they use basically pulse code modulation, PCM. But that is not what we're going to use for our samples in the PlayStation. The PlayStation uses something called DPCM, or even better, ADPCM, which is called Adaptive Differential Pulse Code Modulation, which encodes and tries to compress those 16-bit audio samples using only 4 bits, which is going to give us approximately 1/4 of compression of data, which is quite good, right? For the era where we really need to squeeze audio data and squeeze information so we don't use more data than we need, right, in these limited machines, having 1/4 of audio compression was actually quite good. And ADPCM was very famous, right? And it was used by several consoles like the PlayStation 1, PlayStation 2, PlayStation 3, the Sega Dreamcast. So all these machines, they like to use ADPCM, which is almost like this way of compressing audio data. So it encodes and compresses 16-bit audio normal samples using only 4 bits. And it uses these ideas of, I'm going to give a very high-level explanation. It uses this prediction, this estimation, based on the analysis of the difference of previous values. So instead of recording all the inputs as they are, right, the raw input value as it gets from the signal, we're going to try to do this difference analysis between the previous values and then try to estimate the next one. So we only base on the difference change of those signals that we have, right? So everything that we have is based on the relative value from the previous ones and then the estimation that we predict for the next sample. So this thing right here, just changing and not storing the raw audio input value and storing and comparing this to the relative difference between the previous ones and the next ones, this difference right here is what gets us this compression technique right here, right? So it uses prediction, this estimation, based on this analysis of the difference, right? The relative difference between the previous values of the audio signal that we have. Right, so PCM and ADPCM, this is the one that the PlayStation likes to use. And you will see that one of the most common formats that we're going to store this thing is using a file type called VAG. So this extension VAG is using this ADPCM, Adaptive Differential Pulse Code Modulation technique. So we are going to compress, we're going to convert our audio signals into these VAG files, which is basically this ADPCM format. All right? So don't forget, this thing right here is basically us talking about sound effects, right? So it is usually very small sound effects that we can store with this VAG, and then this file right here, we can just go and send, usually via DMA, to the SPU, or even better, to the DRAM, right, to the memory, sound memory chip, and then that things get buffered and played by the SPU. This is what we do with sound effects. Okay, Gustavo, what happens to longer tracks, right? So what happens to actual music, background music and stuff like that? Well, then we can use different techniques. You will see that we can actually store things as raw audio tracks on the CD, or you can start streaming information, right? So we can stream audio data to the SPU, but then for music, right, for larger audio data, then we can start streaming or using audio tracks. Then we have different techniques. What I'm talking here is basically just using a VAG file for sound effects. We can encode speech, we can encode sound effects, power-ups, engine sounds that loop. So VAG files, they are going to be super useful for us. And speaking of which, in the next lecture, let's just go open our IDE, and let's see if we can convert, let's say, a WAV file that we have stored in the computer. Let's learn how to convert that into a VAG file, right, which is basically using this ADPCM compression right here. And then once we have a VAG file with that voice, we can just learn how via code import, use the SPU library to go and play that sound effect using one of the channels. Right? So I think that's going to be super easy for us to understand if we just look at the code, because then everything is going to come together, right? The idea of using VAG files, the idea of sending things to the SPU, we have to send things to memory, we have to send via DMA, we send this sound effect to the SPU, and then once we get that sample loaded to the SPU, we can just select one of the channels to go and play that sample on the speaker, right? To use that SPU to go and convert things from digital to analog, and then we can actually hear that in the television speaker. All right, so let's just do that in the next lecture. Let's just look at these VAG files and how we can play sound effects with the PlayStation.